Hello and thanks for listening. The goal of the Terran Space Academy is to promote the science of space exploration. Think of us as a virtual space program where we suggest solutions to problems we will all have to solve as we explore and colonize space. We will run the numbers on these ideas together so that we can all know how to evaluate and analyze solutions to see if they are feasible. Sometimes one of you will find an error and correct something we got wrong. This is not a failure for anyone. It is a success for everyone. Finding an error on the ground and working out the details is how we can all arrive at a true understanding of the principles of spaceflight and colonization. Getting things right on paper is the start of getting them right in space. Knowing the relevant equations and concepts will help prepare us all for a bright future in the space industry. We had a great response to the last course on the next generation Starship. Several of you had some great questions and suggestions. Let's address some of these in this lesson on surviving the 9-month journey to Mars. The last lesson had us building our next generation Starship on the Moon, using titanium for the structure and combining plastic with water shielding to make a true interplanetary spaceship. We spun the ship at 4 RPM on its long axis, creating Mars normal gravity on the perimeter of the ship. With a mass of 6,000 tons and a weight on the Moon of 9,720,000 newtons, it is large enough to carry over 1,000 people per trip to start colonizing Mars. And being shielded from excessive radiation exposure, it allows children and young adults to safely make the journey. If you remember, we had an allowance of 1,385 tons for passengers, supplies, and cargo. Let's see if we can stay within that mass and get 1,000 people to Deimos Station, where they will be able to transit down to Mars on Generation 1 starships. At an average of 80 kilograms per person times 1,000 passengers, we get 80 tons of people, leaving 1,305 in our mass budget. Life support systems are critical and often ignored in science fiction films. What does it actually take to keep someone alive in space? And can we design a system for this massive ship that will keep our crew safe? The first rule of life support is the rule of threes. It is not exact, but remember that the average person can only recover without permanent injury from about 3 minutes without oxygen, 3 days without water, and 3 weeks without food. Now, people have survived for much longer, but this is a safe margin and easy to remember. In our ship, we will need to have thermal control, so it doesn't get too hot or too cold. 22 Celsius or about 72 degrees Fahrenheit is usually comfortable for most people. We will need atmospheric control, including oxygen regeneration and carbon dioxide removal, so everyone can breathe safely. Water and food supplies will need to be sufficient for the entire voyage, assumed to be 9 months or 270 days, and we will need a way to deal with waste products. According to my text on the Fundamentals of Space Medicine by Gilles Clement, the average person needs a minimum of the following. Oxygen is 0.83 kilograms per day. Food 0.62 kilograms per day. Potable water or drinkable water 3.56 kilograms per day. Hygienic water 26 kilograms per day, and a total 31 kilogram per day mass per person. Now let's make this work. Water will be recycled, but if we allow 29.56 kilograms or liters consumed per person per day, we should just round that up to 30 kilograms and multiply that by our 1,000 passengers to get 30,000 kilograms total per day. We'll be recycling water and producing it through other means that we'll get to, but to have enough water for 3 days reserve would take 90 tons from our budget, leaving us with 1,215 tons. The recycler on the International Space Station is 90% efficient, and we'll go with that number. If we lose 10% of our water per day, we will need to replace 3,000 liters or 3 tons of water per day. Now, most of the lost water is absorbed into the air and can be recovered with dehumidifiers, keeping the ship's atmosphere at a comfortable humidity level. Let's assume we can recover 80% of our lost water. We still come up short 600 kilograms per day. A 9-month journey, losing 600 kilograms of fresh water a day through the water reclamation system, would need to start with at least 9 times 30 times 600 kilograms, or 162 tons. We are down to 1,053 tons in our budget. The total water mass at the start of the trip is going to be 252 tons. This water will be stored around the habitat areas for more radiation shielding, just as all supplies should be stored around the outer perimeter of the interior of the ship for the same reason. Now, humans actually manufacture water from food and air, so we could get by on a lot less water mass than this. But let's start with this number. Food requirements per day per adult human is determined to be about 0.62 kilograms per day. Let's see how this works out. The average person needs about 2,000 calories or 8,400 kilojoules per day. Food is broken down into the macronutrients, carbohydrates, proteins, and fats. Carbohydrates and proteins have 4 calories per gram, and fat has 9. It turns out that fat is healthier for humans than fast-release sugars, so let's go with a 30-40-30 breakdown to our diet, giving us the following numbers. If we get 30% of our calories from carbohydrates, broken down as half fruits and vegetables for carbs and fiber, the other half tubers and cereals for carbs and insoluble fiber, then 40% protein in soy, dairy, or meat, and the last 30% fats and oils, we get 600 calories from carbs, 800 from protein, and 600 from fats. Since the mass of carbs and proteins are 4 calories per gram and fat is 9 calories per gram, we get 150, 200, and 67 grams respectively for a total of 417 grams per person. Adding water content at 20% mass and 30% insoluble fiber mass, we get 83 and 125 grams added for a total of 625 grams per person per day. Remarkably close to the 620 grams estimated in the text. Let's go with that. Times 1,000 passengers gives us 625 kilograms per day. Multiply that times a 270-day transit time, and we get 168,750 kilograms, so let's round up to 169 tons. Subtracting from our remaining 1,053-ton budget gives us 884 tons remaining. I know we are not adding in a safety margin yet, but let's first see if we can do it at all. Humans burn around 840 grams of oxygen per day on average. If we allow an extra 60 grams per day for heavy exercise and safety, we get 900 grams or 0.90 kilograms. Times 1,000 passengers gives us 900 kilograms per day. If we had to carry all of that, we would have to multiply by 270 and get 243,000 kilograms, or 243 tons. That would leave us with 641 tons in our budget. But we can do better than this. We inhale oxygen and exhale carbon dioxide. If we could convert the carbon dioxide back to oxygen somehow, we could get by with a lot less oxygen and have a backup system for this critical need. Remember that we arrived at Deimos in our last lecture with 20% of our propellant stores in reserve. Our total propellant mass was 4,485 tons, and 20% would be 897 tons, and with a 5.5 to 1 oxygen mass to hydrogen mass ratio, we get 759 tons of liquid oxygen and 138 tons of liquid hydrogen remaining in our ship when we land on Deimos. This is almost 3 times the oxygen we need to keep everyone breathing for the entire voyage. So we will have an emergency supply in case we lose our life support oxygen stores due to a catastrophe. And we might want to put our life support oxygen supply in separate tanks throughout the ship to keep catastrophic loss of the atmosphere due to explosion or micrometeorite impact from taking out all of our oxygen reserve. If our life support systems fail, the reserves of air in a volume of 10,000 cubic meters would only keep all 1,000 of our passengers alive for about half a day. We will also have to remove carbon dioxide from our atmosphere, and we will use a process that will help us generate more water. Water at any time can be broken down by electrolysis for more oxygen and hydrogen. We need to be able to strictly control the carbon dioxide levels on board the ship. Earth's atmosphere is normally 78% nitrogen, 21% oxygen, and 1% argon and other gases, including carbon dioxide. Normal atmospheric pressure at sea level is 101,325 pascals, but let's go with an even bar, or 100,000 pascals. That gives us 78,000 pascals of nitrogen, 21,000 pascals of oxygen, and 1,000 pascals of other gases. Now, in the past, spaceships have traveled with no nitrogen and around 30% oxygen at low pressure. This has worked well for small ships, but we want to maintain Earth normal as much as possible, and nitrogen is valuable on Mars. If we take enough nitrogen to fill a ship the size of ours, how much mass will it have? Our ship had 25,000 cubic meters, minus half for propulsion in the engine bay, minus structural components. Let's go with 10,000 cubic meters of atmosphere throughout the pressurized parts of the ship. Liquid nitrogen has a density of 804 kilograms per meter, but the density of nitrogen as a gas in the atmosphere is only 1.145 kilograms per cubic meter at 300 Kelvin, which is a little warmer than room temperature. 10,000 cubic meters of 78% nitrogen would have a mass of around 8,931 kilograms, or about 9 tons. We take that from the 641 remaining, and it gives us 632 tons. We could also store 55.55 cubic meters of liquid nitrogen for use on Mars and in case of atmospheric loss from the ship. That would be enough to replenish our ship atmosphere 5 times, and nitrogen is needed on Mars. That would be about 45 tons and leave us with 588 tons remaining in our budget. The concentration of carbon dioxide in Earth's atmosphere was about 410 parts per million in 2019. This is the highest content in the last 800,000 years. The level was about 325 back in 1970. This increase has been enough to cause warming of the Earth's atmosphere, but not nearly enough to kill us outright. Carbon dioxide level about 2,000 pascals, or about 2% total atmospheric pressure, will start to cause rapid breathing, headaches, increased heart rate, and cause poor exercise performance. If it goes too high, it can be fatal. A 10% concentration in the atmosphere will cause convulsions, coma, and death within minutes. But this would be about 10,000 pascals of carbon dioxide. More than 30% will kill in seconds. The Apollo missions used single-use carbon dioxide absorbing canisters filled with lithium hydroxide. Having an emergency canister in every living area would be important in case of emergency, but we want to be more efficient. The oxygen regeneration and carbon dioxide removal system on the ISS is based on the Sabatier reaction, and ours will be also. If our average colonist burns 0.9 kilograms of oxygen a day, how much CO2 would they make? The human body burns carbohydrates in the form of glucose, C6H12O6, with 6 molecules of inhaled oxygen to form 6 molecules of carbon dioxide and 6 of water. The atomic weight of carbon is 12, oxygen is 16, and hydrogen is 1. A molecule of oxygen will be 32 grams per mole. A molecule of carbon dioxide will be 44 grams per mole. Hydrogen gas would be 2 grams per mole, and water is 18 grams per mole. If we burn 900 grams of O2 at 32 grams per mole, that would be 28.125 moles of oxygen. The ratio of moles oxygen to carbon dioxide is the same, 6 to 6. So we would have used 28.125 moles of oxygen and get 28.125 moles of both carbon dioxide and water produced. Carbon dioxide has a molecular mass of 44 grams per mole, and that would give us 1,237.5 grams of carbon dioxide produced per person per day. Water has a molecular mass of 18 grams per mole. Times 28.125 gives us 506.25 grams. So human beings can produce over 500 grams of water per day from their metabolism of food. With 1,000 people, that would be half a ton of water production per day. Now, conservation of mass means we end up with the same mass we started with, and we end up with 1,743.75 grams total on the right side of the equation. We use 900 grams of oxygen on the left side, and that means we need 843.75 grams of glucose. Glucose is a carbohydrate, and our diet didn't have that much in carbs, but that is no problem. Our metabolism can turn both protein and fat into sugar, and the body converts what it needs. That is why a diet low in simple carbohydrates can sometimes help you burn body fat. Now we have about 1,238 grams of carbon dioxide to process. There are many ways to extract carbon dioxide from the air. You can compress and freeze it out as dry ice, but there are also batteries that absorb carbon dioxide and build up an electric charge. If we then pull a partial vacuum on the battery with a piston, we can remove the carbon dioxide and, using one-way valves, send it to the carbon dioxide removal system for processing. We should get a little electrical power from this, offsetting the power needed to run the piston system. Carbon dioxide will be removed from the air on our ship using a Sabatier reactor. A Sabatier reactor will use some of the hydrogen from the reserve in our fuel tanks in the Sabatier process. Discovered back in the 1800s. By heating the carbon dioxide to about 350 to 400 centigrade under 30 bars of pressure and exposing it to hydrogen gas over a nickel catalyst. This produces methane and water in the formula CO2 plus 4H2 forms CH4 plus 2H2O by the reaction you see here. Now 1,237.5 grams of CO2 is again 1237.5 divided by 44 gives us 28.125 moles. We need 4 times that many moles of hydrogen. So 112.5 moles at 2 grams per mole means 225 grams of hydrogen gas will make us 28.125 moles or 450 grams of methane at 16 grams per mole and 1,012.5 grams of water at 18 grams per mole. If we double check the mass on both sides of our equations, they match, so we are on track. We now have another 1,012.5 grams or 56.25 moles of water to electrolyze back to oxygen and hydrogen. This will give us 900 grams of oxygen and 112.5 grams of hydrogen. So the reserve tanks are a safety margin in case we lose all of our Sabatier reactors. Maybe a severe solar storm or EMP could shut them down. We also have half the hydrogen we need to put back in the reactor and convert more carbon dioxide to water. And we have converted some of our hydrogen fuel to methane fuel, 450 grams per person per day in fact. With 1,000 passengers, we can generate 450 kilograms of methane per day. Over 270 days, we end up with more than 120 tons of methane when we arrive at Deimos. Now, the ISS throws the methane overboard, but one of the rules of space colonization will be that there is no waste product. Everything is a resource to be reused and recycled. Developing these technologies will benefit those who choose to stay behind. This valuable methane can be used to help land us on Mars with the smaller first-generation starships that burn methane through their reactors. This doesn't affect our launch mass, as we are just converting one thing, hydrogen and carbon dioxide, into another, methane and water. Just like our bodies turn glucose and oxygen into carbon dioxide and water, which gave us about half a ton of water production per day and some energy, which can be used for plants and recycled and offset the reclamation losses. The reason we go through all of this math is that learned opinions can be proven completely wrong when you get down to the equations. Things that seem common sense may not hold up under scrutiny. We have proven that our ship is big enough to safely transport 1,000 passengers with sufficient food, water, and oxygen to Mars, producing 120 tons of methane during the flight. The necessity of a ship this size is that the current Earth-based methane ships will burn almost all of their fuel to get to low Earth orbit. Each ship will require 4 to 6 methane Starship tanker flights just to have enough fuel to get to the Moon or Mars. The Earth-based ships will never have enough radiation shielding to safely transport children and young people for an 8 to 9 month journey. The next generation lunar Starship will solve this problem. The flight to Mars will sometimes have to use the Venus flyby maneuver to help reduce travel time when alignment is not optimal for a direct approach. We would personally love to see Venus up close on our way to Mars anyway. The next generation Starship will be built by a combination of 3D printers and remote-controlled construction robots, using materials mined from the regolith by autonomous and remote-controlled mining vehicles. Please review these lessons to get up to date on those technologies. Now, the optimum design for a Moon to Deimos transporter would actually be either a sphere or a saucer. A sphere is seen here in the classic 2001 movie. There is no reason to be aerodynamic, and a sphere has the lowest surface area for volume, thereby reducing ship mass. I've used our current design to make it easier to compare the next generation Starship with the first generation methane burning ships launched from the Earth and Mars, and because Neopork makes incredibly awesome renderings. We will be able to launch our next generation Starship from the Moon with a thrust to weight ratio of 1.3 at 77% full engine power. That would give us the ability to adjust for heavier or lighter liftoff masses to account for different cargo. The legs of the Starship next generation would have extremely accurate pressure sensors, so that once loaded, the onboard computers could calculate the exact engine power necessary for a safe liftoff. A full engine burn at 100% power would allow us to get a weight of 12,636,000 newtons off the Moon, for a liftoff mass of a maximum of 7,835 tons in an emergency. Let's look at one other issue. Humans have a habit of wasting some food. This organic refuse would be sent to a part of the ship for processing by insects, like crickets. Crickets are an excellent source of high-quality protein for humans, and if we want to survive in space, we have to develop new habits and technologies. Throwing things away will not be survivable. Now, the crickets could be used directly for food, but I think they will also go to feeding egg-laying chickens and fish. Eggs are an excellent food source for humans, and chickens are excellent at turning insects into eggs. Now let's look at another resource: human biological waste. The average human produces between 400 and 500 grams of solid waste per day. Right now, in the ISS, this is sent to burn up in the atmosphere as garbage. But remember, we want to look at everything as a resource. and we'll have watched The Martian, so we know how important recycling can be in space. With 1,000 people producing 500 grams per person or 500 kilograms of solid waste, we would have to have a good way to manage this resource. It turns out that if you combine human waste with just 15% soil, these little guys, red worms, can not only survive but thrive, turning the waste into more worms and usable soil. Some of the worms will be harvested, sterilized, and used to feed the chickens and fish. Another excellent detoxifier of human waste is the black soldier fly. This fly will rapidly start breaking down waste to produce fly larvae, which would again be great for chicken and fish food and human food, but that's a tough sell. During the journey, tons of processed soil will start to build up, about half a ton per day, giving us 135 tons of usable soil to start planting when we get to Mars. So we produced 135 tons of soil and 120 tons of methane on our trip to Mars, while feeding chickens and fish to supplement our food stores and have livestock to use on Mars. Remember, we are spinning our ship along its long axis to produce Martian gravity at the edge of the ship, where we would have sealed tanks for insect and fish production and housing for the chickens. A lot of people had believed we will be vegan on Mars, and I mentioned miniature cows last time. Cows are actually notoriously inefficient, needing around 12 kilograms of grain and lots of water to produce just 1 kilogram of meat at best. But insects are extremely efficient. The cows can come later when we have really large domes and crops to spare. Until then, the colonies will grow spinach, tomatoes, limes, wheat, corn, sweet potatoes, and hemp. Lots of hemp. It makes excellent clothing and parachutes, is very nutritious, very hardy, and grows fast. The seeds and oils can be used by humans and animals, while the fiber has thousands of uses. Our chickens will be producing some of the best fertilizer in the world en route also. We must make use of every available resource to survive the journey and keep our colony growing and safe. Now, we've added about 18 tons of soil we'll take with us, but we are still well within our margin, with plenty left over for inflatable housing and furnishings and other things that we will need for our journey. That's enough for this lesson. Let me know if you see an error or a way to do things better. Don't forget to like and subscribe. Help support us on Patreon if you can at patreon.com/Terran Space Academy, and stay safe. At Astra Pro Terra.